Up until now, we've been working with Euler networks, and Euler was considering what happened as you crossed each edge exactly once. So we have Euler paths and Euler circuits, where we're considering crossing each edge exactly once. Now, what if we didn't care about the edges? What if we didn't care about going up and down every single street exactly once? What if instead we changed the rules? Rather than passing through each edge exactly once, what happens if we just need to cross each vertex exactly once? And so that's what we're going to look at here. Why can't I edit this? Come on. There we go. So rather than looking at each edge, what if it's all about the vertices that count? Now, this is inspired by an Irish mathematician, William Hamilton, and he was looking at what he calls the traveling salesman problem. The idea is that a person leaves their home, they need to travel around to different cities, and they want to return back home. Now, they want to do this in the most efficient route possible. You don't need to go every single road between each city. You just need to go city to city to city back home. Now, there are different ways of getting to each city, and the order in which city that you travel to, that's the question that Hamilton came up with. Not Hamilton from the play or the $10 bill, but this is Hamilton. We define what we call a Hamilton circuit as a circuit that begins at any single vertex, travels through every other vertex exactly once, and returns back to the starting point. Now, there are no rules like there were for an Euler circuit where we had exactly 2 odd vertices or 0 odd vertices giving us an Euler path and an Euler circuit respectively. Hamilton, we need to play around. Here, we have 2 graphs, then we're going to try to find a Hamilton circuit on each. The idea is starting anywhere at any vertex, we're going to go to each other vertex exactly once and return back to the starting point. So our graph on the left, just without anything, I can start at vertex A. Now we need to go all the way around and get back to A. Circuit returns back to the start. I can start by going to E, to F, to D, to B, to C, and back to A. I've created here a Hamilton circuit. We go all the way around. We can see that we've traveled all the way around. We've hit every single vertex, every single city without repeat. Each city has one in and one out. One in, one out. One in, one out. We don't care about the edges. So here, we don't cross that edge. We don't cross the edge B to F. We don't cross the edge A to B. We don't need to do that. Hamilton circuit is just concerned, hit the vertices, get back to the beginning. If we look at the graph on the right, well, we can start at A, go to C, go to D. Nope, don't want to go to B. So A, C, D, E. But here's the problem. We're at E. There is no way to get to B without returning back to D. So we've gone A, C, D, E. We're stuck at E. Going back, we'd have to repeat. So clearly, we cannot follow that route. Instead, maybe we go start at E. Well, if we go E, come on, where are we? If we go E to D to B to A to C, we're stuck again. We cannot get back to D because we've already been into D. We've already gone into D once and then we've left D. We cannot go back in again. So each vertex needs to have, and I'm going to draw your attention back to the left graph. Each vertex has exactly 2 highlighted edges connecting. We've already got 2 highlighted edges connecting D in the right graph. As soon as we tried to return back to E, that's not okay. That violates our rules. So the graph on the right as a whole, we cannot create a Hamilton circuit because of that point E. Not that there's a rule, but we can figure it out that anytime we have something where we cannot return or there's only one way in or out, we're stuck, we cannot have a Hamilton circuit. Now, from here, Hamilton was concerned with how do we travel around. So imagine that we're going to go on a business trip. We're going to leave New York City. We live in, we live in Philadelphia. We need to travel to New York. We need to go to Pittsburgh. We need to go to Cleveland and all the way back home. We want to do this in a way that minimizes our total distance. If we add together everything that we have, we can start at Philadelphia. We can go to, draw this in, we can go to New York, we can go to Cleveland, we can go to Pittsburgh, we can go back to Philly, making that circuit. If instead we go from Philadelphia, maybe we want to go all the way to Cleveland, back to New York, back to Pittsburgh, back to Philadelphia. Now, just anecdotally, that looks like it's definitely longer. Instead, New York to Cleveland, well, we can go Philly to Pittsburgh, maybe to New York to Cleveland, and all the way back. It's actually the same thing, just in a different order. There's one more. What are we missing? If I go from Philly to New York to Pittsburgh to Cleveland, back to Philly. There's actually 3 different routes, and what we would have to do is we need to check each of the 3. Now, how can we do this? What we look for is I'm going to consider the road mileage here. I have a map, or rather a table, that tells me all the mileage from one city to another. So this first line is saying we're starting in Cleveland and we're driving to New York, cost us 473 miles. Or starting at Cleveland, going to Philadelphia, cost us 413 miles. Starting in Cleveland, ending in Pittsburgh, 129 miles. So forth. New York to Philly, New York to Pittsburgh, and I omitted New York to Cleveland. Now we notice that New York and Cleveland, we have this symmetry in our graph. Well, that's because driving from Cleveland to New York or driving from New York to Cleveland is exactly the same. We're just going backwards. What we would have to do in solving the traveling salesman problem, where we need to make our way around, is we need to figure out how are we going to go through there, all those lines. We'll use the distances. We'll take these, and since I have 4 cities, 4 vertices, I'm going to create what's known as a complete weighted graph. Now, a weighted graph is one where each edge, rather than just being a connection point, it has some weight associated with it. Each of these would be the weights of those edges. And we're saying that we begin in Philadelphia, down here in the bottom right. I could travel to New York, could travel to Pittsburgh, I could travel to Cleveland, and from there, we can keep on branching out. Our task is to find the shortest route. We're also using here, I mentioned, a complete graph. Between each edge, or excuse me, each vertex, there is an edge that connects to every single other vertex. So that's the idea that we're at a specific city, we can go to any other city. From Philly, we can go to New York, we can go to Pittsburgh, we can go to Cleveland. From New York, we can go to Cleveland, we can go to Pittsburgh, we can go to Philly. From Cleveland, we can go to New York, to Pittsburgh, to Philly, or from Pittsburgh, we can go to New York, to Cleveland, or Philly. Each one connects to every single other one. And what we have to do here is we need to try every single avenue. So I'm going to label these A, B, C, and D. There are 3 different ways that we can actually travel through this. Thinking back to those of us that took statistics, this is a permutation, a factorial. Now it's n minus 1, and we're also going to divide by 2 because each way is symmetric. Going forward is the same way as going backwards. When we have 4 vertices, there's 6 different ways, which means there are 3 different ways that we can travel a route. And it grows exponentially, as the factorial notation does. We'll talk more about that later. Now, if we're going to find the shortest possible route, we need to figure all the different combinations. This is the way. Starting at A, we could go to B, we could go to C, we could go to D, back to A. And we would take those distances, 101 plus 473 plus 129 plus 288, and we're going to get a weight for that. So what did I say? 101 plus 473 plus 129 plus 288. Or, rather than A to B to C to D, we could go A to C to B to D back to A. Different route. A to C to B to D to A. A to C, we're going to go 413 miles. We're going to add 473 miles. Then we're going to go to Pittsburgh for 368 miles, back to Philly for 288 miles. Or one final option. We could go A to D. Nope, that's the same one. I'm going to say, and I was about to say, A to D to B to C to A. We've done that already, just going backwards in the last one. A to B to C, A to D to B to C to A. There's one more, and what are we looking for? We've gone this way, A, B, C, D, A. I like to look that there's a chevron there. We've gone A to C to B to D, back to A. I see there's an arrow pointing down to the left, up to the right, or, there it is. One final way that we could travel. Get a different color. We go A to B to D to C, squishing A, D inside there. That way, A to B to D to C, back to A, would cost us 101 plus 368 plus 129 plus 413. Quite a bit in there. But that's the way we have to do it. We need to try out each individual one. So at this point, I'm asking you, take the assigned practice that's on there. I'm asking you to find whether or not we have Hamilton circuits. Can we find our way around the graph, crossing each vertex exactly once, or why is it not possible? So you're going to identify, is there some point E or some edge that we cannot repeat? Then I'm asking you, given some graphs, can you find the different combinations? And if we add those together, what's the smallest value that we can get? Good luck. I'll post the solutions soon.